Hello guys, welcome back to another episode of Consultant Explains Maths. Today, I'm making a new video after I think weeks of my last video. I mean, it has been the habit of this channel anyway, because I have a full-time job and I couldn't really dedicate my time to keep solving problems, especially problems that I could not solve in university. And it has been the theme of my channel, especially in the Consultant Explains Maths series. And I have had tons of questions from university that I could not solve, and I probably should bring them all here. But that would take too much time because I couldn't really dedicate enough time to think about solving those problems. Wait, hold on, I just repeated myself. Whatever. Anyways, I'm making a return by something easy, hopefully. In fact, this is probably appropriate for senior high school schoolers. So we have this problem here. Suppose that we have two polynomials, x squared plus mx plus n equals 0, and x squared plus px plus q equals 0. Now, if both polynomials have a common root, we want to prove that the following relationship holds. Prove that this is an n minus q squared minus m minus p times np minus mq equals 0. Right. Give it a try, and I'll come back with a solution. All right. Enough time. So I told you before that this is going to be an easy question, and you can actually see why. But in case you don't, it lies on the definition, or rather the representation of what a root is. I'm not even sure if it's actually a definition, but well, it might as well be. So recall what a root is. Recall what a root of polynomial is. So for instance, if you have a polynomial, like let's just start simple, x squared minus 2x minus 3 equals 0. The roots of this equation can be obtained by factoring it. So it's x minus 3 for x plus 1. And then you have x equals 3 and x equals -1 as the roots of this polynomial. Now recall that if you substitute the roots into the original polynomial, you'll obtain 0, which is equal to the right-hand side. So for instance, if you were to put 3 in place of x there, substitute 3 with x, or x with 3, you'll obtain 9 minus 6 minus 3, which is equal to 0. Similarly, if you plug in -1, you have -1 squared minus 2 times -1 minus 3. So you have 1 plus 2 minus 3, 0. Now, this representation is useful for this problem. Now we want to suppose that the common root is r. So what this means is if you plug in r into both of the equations, you obtain 0. So r squared plus mr plus n is equal to 0. And so is r squared plus pr plus q equals 0. Because these are zeros, you can basically connect the two equations and obtain r2 or r squared plus mr plus n equals r squared plus pr plus q. Now notice that we have r squared on both sides, so we can cancel those out, leaving us with these two polynomials in first degree polynomials. And then we can move PR over to the left. R minus PR equals Q minus N. And you can factor out R from the left-hand side. R times N minus P equals Q minus N. And this means that common root, we didn't know what the common root is. We just supposed there is a common root, and it's denoted by R. But we now know the precise value of R, which is Q minus N over M minus P. Okay, so where do we go from here? Well, now that we know the common root, we can simply sub that common root into one or two equations. It can be either of the two. It doesn't really matter which you choose. For this demonstration, I'm going to go ahead and show that if you plug it into the second equation, you'll obtain the desired result. So right. Okay, can't even remember. Q minus N over M minus P. Q minus N, M minus P. I'm going to denote this as 2. Substitute 2, 2. Right, just a bit of a heads up there. Q minus N and M minus P. Plugging this value into the second equation gives you this, plus P times Q minus N over M minus P plus Q equals 0. From here on out, it's just algebra. You simply do a bit of a tedious calculations, and I hope you can actually calculate this on your own. So let me just do the full calculation myself. Oops. Now this is just arithmetic of fractions, and it's quite easy to see from here how this will turn out. But this to hold, for this kind of a equation to hold, you can verify that the numerator does indeed value it to 0. Sorry, I mean like the numerator should be 0. So Q minus N squared plus P Q minus N and minus P plus Q. These PQ cancels out, and we obtain, because Q minus N is equal to N minus Q, Q minus N squared is equal to N minus Q squared, we can flip the two seamlessly. M minus P, and just to stay true to the actual thing that we need to prove, we can multiply the the right bracket here by -1. Basically, we want NP to be in front. So if there's a negative here, we can factor out -1 to get negative n minus p. Oh, hold on, it's exactly m minus p times np is mq, which is the desired result. There are definitely variations of this problem, which is just, well, varying what coefficient is the same across the two polynomials, or even by adding the degree of the polynomial. So instead of x to the power of 2, we would have x to the power of 3 plus b x to the power of 2 plus whatever. But really, it's just going to be more the same, and the algebra is only getting even more tedious. That would be the only real differences if I were to modify this kind of problem. But now you get it. So I feel like that's about it for this short video. I really hope you enjoy it, and leave a like and subscribe if you feel like it. Bye.